about metastability in periodic XY chain. Please, Assaf.
Okay, sorry. So hi, thanks for the invitation. So I'll talk about topologically induced metastability in a one-dimensional XY model. Maybe a few words before I start about XY model and what is topological effects in statistical physics. So I don't know how much you know the XY model and the topological phases, but okay, since the works of Costas and Taudis in the 80s, people noticed that topology or topological arguments play a very important role in many systems in statistical physics. And even won the Nobel Prize a couple of years ago for this realization. And what Costas and Taudis found out is that in probably the most important model that has a topological effect in statistical physics, which is the XY model in 2 dimensions, there is a very specific phase transition, a very special phase transition that occurs when some topological properties of the system change. Now, this is a very complicated phase transition, and understanding it mathematically is very involved. Not completely impossible. But what we were interested in this project was understanding the dynamics of models with this non-trivial topological properties. And in order to do that, the 2-dimensional case is extremely complicated. So we took a toy model, which is a 1-dimensional XY model that I will now introduce. Okay, so what is the XY model in our case on a periodic chain? We have n spins, x0 to xn-1 or x1 to xn, and we put them on a circle. So you see that x0 equals xn, and each of these spins points at a direction on the circle, so it belongs to S1. And this is how a configuration of our system looks like. So each configuration has an energy, which is given by this Hamiltonian. So you have minus j. J is a coupling constant. And then for each 2 neighbors, we take the cosine of the angle between them. So the cosine of xi minus x minus 1, we sum all of that. And, energy is always defined up to an additive constant. And I added the plus nj at the end just because it would be a bit nicer further on. Okay, so we see that if we take j to be positive, the interaction is attractive. What do we mean by attractive? For the energy to be small, the system always tries to be in a smaller energy state. We need this minus j cosine of difference between angles to be small. So the cosine has to be large, which means that xi and xi minus 1 should be very similar. So the spins are attracting one another. It's an attractive interaction. Okay. So once we have this energy function, this Hamiltonian, we can define the equilibrium measure, which looks like this. So the probability of a state x is proportional to exponential minus beta h. And I don't know how much all of you are familiar with this type of distribution, but I could just look quickly what it means. So beta is called the inverse temperature. So it's really 1 over the actual physical temperature. And we see that if a state has very large energy, then this exponential minus beta h is very small. So it's very unlikely, while states that have a very small energy are much more likely. And okay, so we see that this inverse temperature, this beta, captures how much the energy is, the importance of the energy in our measure. So large beta means that energy is very important. Small beta means that states with similar energy would still have similar probability. So this is the equilibrium measure. And okay, this is a general effect in statistical physics that one-dimensional models are trivial. And by trivial means that if we'll take a very large system and we'll look at it from far away, it would behave essentially the same as if all spins were independent. So nothing interesting happens. In order to overcome this issue, since we want to work in one dimension, we'll take beta and j to infinity. So our beta and our j have to depend on n, and they would go to infinity as n goes to infinity. And this way we can hope to see some non-trivial behavior. Okay. So, sorry. So we see that if beta and j are very large, then this exponential minus beta h is going to be very, okay, also very large when or very small when the energy is small, and very large when the energy is large, which means that our equilibrium measure would only feel the states that have low energy. In general, when we have a large beta or low temperature, the system goes to states with very small energy. So the first question we ask is, what are the low energy states? So let's write again the Hamiltonian. So this is the energy. And we see that the lowest possible energy is when all cosines equal 1, which means that all x's are equal. So all spins are aligned. And this is the ground state. So the minimal energy state is the ground state. Okay, I write ground state. I should have written the manifold of ground states, but we'll ignore this point. It doesn't really matter. So the ground state, the minimal energy state, is when all spins are aligned. But there are other local minima where the energy is also small, even though it's not minimal. And we have n local minima. You could see 3 of them here. So the first one to the left, we see that the distance between the spins is not 0. So the angle between neighboring spins is not 0, but it's still very small. It's 2 pi over n. If we go to the second one, it would be minus 2 pi over n. So, okay, same thing. In the third example, the k equals 2. The angle between 2 neighboring spins is twice times 2 pi over n, which is larger, but still, if we're thinking of a large system of n, which is very big, then it would still be a very small energy. Okay, so these configurations for each k are described by the angle between a spin to the next one is 2 pi k over n. And okay, so and these are local minimum. So each configuration that looks like this is a local minimum of the energy. Now we see here that k is some parameter that allows us to characterize this minima, and this is the winding number of the configuration. Okay, so each of this minima is characterized by its winding number. We could actually define the winding number more generally for other configurations. So if we take any configuration, x1 to xn of spins, and then we take the angle between 2 neighboring spins, and we sum all of these angles. Since we're in a circle, we end up with something which is 2 pi times an integer. So we divide by 2 pi, we get an integer, which is called the winding number. Just this tilde that you see above this xi minus xi minus 1 is because angles are only defined up to 2 pi. Let's say going pi over 2 to the left or going 3 pi over 2 to the right is the same thing. But when we define the winding number, we always want to take the shorter path. So we would go pi over 2 to the left rather than 3 pi over 2 to the right. So this tilde means the representative of this angle, which is between minus pi and pi. So we always take the shorter path. So And we sum all of the distances that we passed, and in the end, we get the winding number. Okay. One thing that we could note is that the winding number is not defined everywhere, because if the angle between two spins is exactly pi, so if I have two neighboring spins that point in exactly opposite directions, then I don't know whether I want to go clockwise or counterclockwise, right? Because the distance is the same. And in this case, the winding number will not be defined. But okay, this is a set of measures 0, so the winding number is defined almost everywhere, even though it's not defined everywhere for all configurations. Okay, then now we understand what the winding number is, and we could calculate the energy of the minimum, of the local minimum with winding number k. You see here the calculations. So we have minus j times n, because we have n pairs of neighboring spins and edges. And the angle between two neighboring spins is 2 pi k over n. So we take the cosine of that. And if we imagine that k is fixed and n is very large, we could take an expansion of the cosine, and we get this 2 pi square j k square over 2n. So we understand approximately what is the energy of each of these local minima. Okay, so I'm writing this again here, multiplied by beta, because we have a beta h on the measure mu. So if you remember, our equilibrium measure is proportional to exponential minus beta h. The expression minus this expression here, so 1/2 2 pi square beta j over n k square. And we see that there are two regimes here that interest us. Now, the first one is when beta j is much larger than n. This means that even passing from k equals 0, the energy is 0. This is our ground state. But if beta j is very large, then even k equals 1 or minus 1 would have extremely high energy. So all states except for k equals 0 have a very low probability. So the winding number will be 0 with very high probability. On the other hand, when our beta j is much smaller than n, then if k is 0, 1, 2, 10, they would all have comparable probabilities. So we'll see something which looks like, so the winding number looks like a continuous random variable, right? Have a very large range. So even though it could only be an integer, it looks from far away like a continuous variable, which is normal because we have this coefficient times k square, the exponential. It's just a normal random variable. Let's see this on this graph. So let's see. Below order 1, when beta j is smaller than order 1, we said that the model was trivial, and we don't look at this regime. Okay. Between order 1 and order n, the winding number looks like a normal random variable with the variance given by this expression, so 2 pi square beta j over n. And when beta j is above order n, the winding number is 0 with very high probability. Okay, there are no questions at this point. I'll go on to the dynamics. This was only the equilibrium. Until now, we understood the equilibrium of this one-dimensional periodic chain with XY spins. I started with saying that we wanted to understand the dynamics. So we put the dynamics, which is the Glauber dynamics, or gradient descent, if you want, which is defined as the following Ito equation. So we see that dx is proportional, is minus gradient h, which means that I go down the gradient, so, which makes sense since I want the energy to be small, plus some noise term, sigma dBt, and the noise, the strength of the noise is 1 over 2 beta, which guarantees that this process is going to be reversible with respect to the equilibrium measure, mu, that we talked about before. So this is a dynamics whose equilibrium is really our equilibrium. I think I thought of the Glauber dynamics for this model. Now, unlike the equilibrium, where we want to understand the lower energy states, in order to understand the dynamics, we need to look at the entire energy landscape, which we'll try to do next. So what do we know? We know that we have these n minima, right? That k equals 1, 2, 3, etc. So here there's a caricature of n minima. And the difference between two minima, okay, these minima are on a parabol, right? Proportional to k squared. And the difference between two minima is of the order j over n. So this is what we know so far. When we have this type of system, where we have several minima and a very low temperature, right? Because we take beta, which is very large. Remember that we're always in a regime where beta j goes to infinity. What typically happens is metastability phenomena, which means that our system would spend a lot of time near some minimum, because this, if you remember, we had this minus grad h term in our dynamics, which is going to pull us in the direction of the minimum. But then occasionally we would be able to go far away from the minimum and maybe land in the neighborhood of another minimum. So this is how these type of processes usually look like. And the question that we ask is, how long does it take for the winding number to change? So to move from the neighborhood of one minimum to the neighborhood of another minimum. Okay. To answer this, we start with a very nice observation. The winding number, if you remember the definition, it was just sum of differences of angles, so it's a continuous function. And it's an integer. So if you have a continuous function which is also discrete, it has to be constant on each connected component of its domain. Which means that if our winding number changed, if we moved from one configuration to the other with a different winding number, then at some point we had to pass through a configuration where the winding number is not defined. Remember, we said that it's defined almost everywhere, but not everywhere. And actually, these very particular points when it's not defined, when we have two spins that are exactly opposite, even though they have measure 0, during the dynamics, in order to change winding number, we have to pass through one of these configurations. So at some point along the path, we had two spins pointing in opposite directions. So xi plus 1 minus xi equals pi. And this means that we have a certain energy barrier. What is the S energy barrier? So when I have the two spins pointing in opposite directions, the angle between them is pi. So the contribution to the energy given by this couple is cosine of pi, which is 1, okay, minus beta j, never mind, or minus j times 1. But near the minimum, they are very close together, so the angle is, okay, not exactly 0, but more or less 0. So the contribution is minus 1. And overall, the difference between the two is 2j. So the energy barrier is 2j. The energy of this specific state that we have to go through in order to move from one winding number to the other is 2j. Okay, so we see it in this picture. So we have the minima that we already had. We have this difference j over n between two minima that we had before. But now we also know that the difference between a minimum and a maximum, between a local minimum and a local maximum, is 2j. Again, when n is very large. Okay. So we understand how the local minima look like. We understand what the energy barrier is. So we can describe the time it takes to move from one winding number to the other. So, okay, we know the energy barrier is 2j, and we know that in order to pass this barrier, we have n possible spins or n possible edges or neighboring spins where we could overcome this barrier. So either the angle between 1 and 2 is pi, or 2 or 3, or 3 and 4, etc. Have n options to overcome this barrier. Which means that the entropy of this transition state is given by log n. Right? The entropy is log of the number of options that we have. Okay, and now we're ready to say what is the time to change the winding number, and this is going to be exponential of the free energy. So 2 beta j, the 2j comes from the energy barrier, minus log n, which comes from the entropy barrier. Okay, simulation. Let's see, so I need to stop sharing and share another screen. Okay. So you see here the dynamics. We started at winding number 1, and now it's jumped to 0. You see that the spins are aligned up to some fluctuations. And I don't know if any of you noticed the point where 2 neighboring spins pointed in opposite directions. So run it again and try to find the 2 spins that point in opposite directions. Let's see. Do you want to another shot or? Okay, I'll put it again. So again, I'm sorry, you see here the winding number is 1, right? Because when you do an entire tour around, let's say, if you go counterclockwise and you follow the spins, then you have 1, then they move, one round. And now they flipped. Okay, so now I'll show exactly where they flip. So this is the same video, but I added small circles around these 2 spins, and you see that at some point they have to point at opposite directions now. And this has to happen in order to move from one configuration to the other. And you see that this is very difficult to do, right? Because of this minus grad h, or because of this energy barrier, it's very difficult to bring 2 spins to point in exactly opposite directions, which means that it takes a lot of time to change the winding number. Okay, so I'm actually have the feeling that I'm going a bit fast, and so since I don't have a lot to say, but just I know that there are supposed to be some plenty of students. How familiar are you with this idea of the time to change state is exponential with the free energy barrier? Is something that I should explain, or is it clear for everyone?
You can explain.
I can explain. Okay. So let's go here. What is the energy barrier? How can we interpret this energy barrier? And if I go back to the definition of the measure, so you see that the measure is proportional to exponential minus beta times the energy, which means that if I have 2 states, let's say low energy states, or the minimum versus the maximum, the energy barrier is the exponential of the energy barrier gives the ratio between their probabilities. So if I have high energy, okay, if one state has energy which is let's say the maximum has energy j more, 2j more than the minimum, then the probability of the maximum is the probability of the minimum times minus e to the minus 2j, 2 beta j, which is much smaller. And actually, if we imagine that beta and j are very large, so that most of the time or most of the probability concentrates around the minimum, then we could also say that this exponential minus energy barrier is the probability of the maximum conditioned on being in a certain winding number. Okay, so if I condition on having winding number 10, I will spend most of my time near the minimum belonging to the winding number 10. So my probability to have winding number 10 is more or less exponential minus beta h 10. And if I know that I'm there, then the probability to have winding number, to have the probability to be near this this maximum, to have two spins pointing in opposite direction, is going to be exponential minus energy barrier. Okay. So exponential minus the energy of the maximum divided by energy of the exponential energy of the minimum, which is exponential of the energy barrier. So we could think of exponential of the energy barrier as the probability to be at the this transition point, to have two spins at opposite directions, given that we're in the neighborhood of a certain, of a given winding number. This is the way to think of this energy barrier. And I say energy barrier, but actually we don't just have exponential minus beta h, right? We have a density, the Lebesgue measure. And this is where the entropy comes in, because if we have n different positions where we could have where two spins point in opposite directions, then the volume of this transition state is n, right? We have n options, so we have n times exponential minus beta h. It's not just exponential minus beta h, which adds this this log n. So if we think of this exponential minus barrier, minus free energy barrier, so the thing that that we see here, so exponential of minus that as the probability to be on this transition state, on this bed, on this local maximum. And we imagine that, most of the time the system is at the minimum. Then maybe it tries to go to the maximum. The maximum is very unlikely, so it's probably going to fall back to the minimum. Then it's going to try again and fail again and drop again. And if we try many times, the time it would take to succeed to reach this this local maximum is going to be more or less 1 over the probability to be at this position, which is exactly exponential 2 beta j minus log n.
Assaf, sorry,
Yeah?
there is a question in the chat.
I for some reason can't see the chat. So could you?
So why can't you change W adding plus C in each difference of xy minus xy plus 1? Why do you need a breakpoint to change W?
So let's look at the definition of W. Maybe this. So I take each two neighboring spins, and I see how much I need to rotate in order to move from one to the other, right? And then if I could rotate to the left or to the right, and they do something like that, and in the end, I could do an entire circle or 2 or -1 or -2, and this is going to be W. And the problem is that, the reason for this still in the definition is that in order to go from here to there, I could do either this or that. And the point is that we always have to take the shortest path. So I don't know if it's clear. We always have to take the shortest path. And when two spins are in opposite direction, we don't know which path to take. And then this W is ill-defined. And since W is continuous and discrete at the same time, it can't change unless it's ill-defined. Is this better? And actually, this is a crucial point, because this is the reason that we call this metastability topological. Because W, the winding number, is a topological property, so it doesn't change under homotopy. It's a discrete object which is also continuous. The topological input is that we have something which is both discrete and continuous, and this means that it's a constant. And if it's a constant, then the only way to break it is if we go to this domain where it's ill-defined.
So may I ask a complementary question to this one on the chat? Maybe this helps a little bit. So in the simulation that you show, at some point you have these spins pointing in opposite directions and breaking the the cycle to go from winding number 1 to winding number 0, right?
Yes.
And wouldn't be possible, for example, for 3 neighboring spins to collaborate in some weird way to break the cycle but not just a break. I mean that the break happens in 3, like 3 guys doing a triangle instead of 2 guys doing opposite directions. Or that is super costly energetically or exponentially, and you can just discard this type of situation.
No. So if you look at this definition of the winding number, it's a continuous function as long as all the configuration is in the domain, right? Because this lift is a continuous thing. It's an open set. It's an open interval, so I can define the lift. So this winding number is a continuous function of the configuration. And if it's continuous and discrete, then it could only change when I leave the definition domain of the configuration. And the definition domain of the winding number. And the only configurations where the winding number is not defined are the ones where I have somewhere 2 spins in opposite directions.
Okay.
So
one has to be convinced of this combinatorial fact somehow that it's not so obvious at first sight, maybe.
So if you think of maybe you need to really think of the fact of the continuity of this winding number, right? Because the domain of the winding number is an open set. Okay, you need to understand that this is an open set. That in this open set, this winding number is continuous because if you change the configuration a bit, then this lift operation remains continuous. Then you take differences are continuous, sums are continuous, or everything is continuous. So this winding number is continuous in its domain. And then, you need to convince yourself that it's an integer. And this is due to the periodic boundary conditions. By the way, if you take the same model, but without periodic boundary conditions, so you take a free boundary instead of periodic, you will not see a metastability effect. This entire thing relies very heavily on the fact that the winding number is an integer. If you have a setting where the winding number could be any real number, then this effect will not happen. Okay, this is really a topological thing. So a recap, or if people have other questions. Okay, so actually essentially at the end, so we say that the time of change W is this exponential of the free energy barrier, which came from the probability of this local maximum. And if we look at this formula, then we see that if my beta j is larger than 1/2 log n, then the time to change the winding number is very long. Let's say it's 1/2 log n. So if beta j is 3/4 log n, and I take n to be very large, then the time to change, then the time that I stay in a given metastable state, in a given winding number, is going to be very long. On the other hand, if beta j is smaller than 1/2 log n, then the time to change winding number is going to be extremely fast. So the second I enter a certain winding number, I'll leave it, and there is no long-lasting topological order. And if we compare it to the equilibrium, we see here everything in the same place. We see that we discovered a very large regime that we didn't see in our analysis of the equilibrium, because when we talked about the equilibrium between order n, order 1, and order n, the winding number was just approximately a normal random variable, and after n it was 0. So in a sense, you only see the topology when beta j is larger than order n. Right? Otherwise, we don't really see a winding number. It's just a normal random variable. We see that there is a winding number, discrete winding number only at order n when it's forced to be 0 because even 1 or 2 are too large, if you remember. But if we look at the dynamics, we see that we have an entire regime between 1/2 log n and up until order n, where equilibrium doesn't see any topology. So from the equilibrium point of view, there is just nothing happens. We see a random, more or less random, a normal random winding number. But if you look at the dynamics, then actually, when you prepare the system at a certain state, it would stay with the same winding number for a very, very long time. So if we're thinking about what we will actually measure, we're not going to measure this this normal random variable that the equilibrium gave us because, okay, unless we wait for very, very long times. It means that we have this metastable states which persist, and this is something that we don't see in equilibrium. So the topology, in a way, is manifested in the dynamics over much, much larger scales than in equilibrium. So this is more or less the story that I wanted to tell. And now there are plenty of questions. So this is really a small toy model that shows that there are interesting things that could go on from the dynamics point of view coming from topological effects. But there are many questions. So first there is this model. And I said that the time is more or less exponential to beta j minus log n. This is not very precise estimate. So there are techniques to study metastability that could get much more precise estimates, but okay, of course, they're much more complicated, and okay, there are issues that could come up. But in principle, I would say that it could be possible to find a more precise prefactor of this exponent. Maybe a bit more interesting is to look at log time behavior, because this time that we found, this exponential 2 beta j minus log n, was the time it takes to jump from one winding number to the next one. But then if we continue waiting, then the winding number could go back to where we started, or jump to a third one, and then go back. So what we expect is to see some type of random walk. We could grow by one or decrease by one at times which are off this scale, this exponential free energy barrier. But okay, in some process which we think should be just a simple random walk with jump rates 1, but with exponential jump rates of rate, with exponential jumps of rate 1. Sorry. Of course, this is not that simple to show.
So why do you have can I ask you, why do you have in your picture these very short excursion, very small jumps?
These are jumps that didn't succeed. So there are two spins that got very far, that got up to distance, which is pi. Okay, and of course there are some inaccuracies of the simulation, but two spins that point in opposite directions. Then they oscillate a bit. So you have winding number that changes between 0, 1, 0, 1, 0, 1. And then they decide whether to go to the left or to the right, or whether to stay or to change. So these small lines are exactly these points where I had two opposite spins that oscillated a bit because it's a local maximum, right? So you could go left and right more or less freely. So there are some oscillations, and then they choose where to go. So you see, actually, in all changes, there are some oscillations first, and then sometimes it oscillates without changing. Yeah, so this is something that you could see actually in this simulation. One thing that, okay, I didn't put the graph here, but you could actually see in similar simulations that the jump time is an exponential random variable, which is what we expect, but we don't know how to prove it. And okay, the conjecture is that it's going to be a random walk. And if you want an even braver conjecture, then if you continue to look from far away until this random walk converges to a continuous process, then we think it's going to be an Orson-Uhlenbeck process whose equilibrium measure is given by this our equilibrium measure for the winding number. So this where is it? This square root, this 2 pi square root beta j n winding number is normal of 0, 1. Okay, but we're not there yet. So this would be a nice question to study. What is the log time behavior of this winding number? Another thing is to study the metastable states, because once we know that the system lasts for a very long time at a given metastable state, then we could ask how it behaves in this state, right? What are the correlations? Let's say I apply a small field, so I try to pull the spins to the right, but with very small field, and ask how do they react. So if the winding number is 0, we would say that if I try to pull them to the right, then just all of them would point on average to the right, and okay, everybody's happy. But if the winding number is 1, then they can't all point to the right? Because the spin at position 0 and the spin at position n/2 point in opposite directions. So something else has to happen, and okay, what we think and what we see in simulations is that the metastable state with winding number 0 reacts much more to external forces than the metastable state with winding number 1, which reacts much less. So this is, I think, an interesting thing to understand. How does the metastable state itself behaves? Then, the big question is, how does XY model behave in higher dimensions? And in particular, in 2 dimensions, we know that already equilibrium has this topological phase transition on a finite temperature. So we don't need to take beta j to infinity. And there is a phase transition where vortices are formed or not. And then you could ask what happens if you put dynamics on top of that, right? So do you have some metastability of vortices? Maybe yes, maybe not. Maybe it depends on the boundary conditions. And, okay, so this is completely open. When we introduced this model, the hope was to maybe motivate or give some idea of what could happen in two-dimensional XY model. And then, okay, once we finish with XY model, we could ask what happens in a general ON spin model, which means that instead of taking spins on the circle, on the one-dimensional sphere, we allow them to live on a two-dimensional or n-dimensional sphere, and see and then the topology changes completely. So the winding number is going to be replaced by some second homotopy group or a second co-homotopy group, and okay, everything complicates, but we still expect to have topological effects in some situations and no topological effects in other situations. And I think it would be very nice to understand what happens in more generality, in more models, and to characterize the different possibilities. So that's it. That's all I wanted to tell you.
Okay. Thank you, Assaf. Is there any question?
Yeah. Well, have you analyzed your model when you fixed n and you send beta to infinity?
We didn't write anything, but this should fall under very standard metastability results. So I think in this case, let's say the exponential jump times are almost free. The random walk picture might be more difficult. In this part, we really wanted to understand the n dependence and to get this, you see this 1/2 log n transition. Yeah, so fixing n and taking beta to infinity to study things like this this exponential jump times or the random walk picture should be doable. We didn't try that hard because somehow I think it's the interesting domain is this domain between 1/2 log n and order n. So it misses some of the interest, but it could still be a nice result. Actually, okay, this is maybe for later, but maybe you could take, let's say, beta, which is 100 log n instead of 1/2 log n, and to say interesting things. Yeah, this would be a more, let's say, if we're interested in this random walk picture, this might be a more doable model or regime.
Okay, thank you. Other questions?
So may I complement Claudio's question a little bit? So if you take something like beta equals to epsilon n or something like that, probably you expect the law of the winding number to converge to something to the discrete random variable.
If I take
if you take something around the theta n regime, something like, I don't know, a small constant times n or something like that.
Yeah, it's a discrete Gaussian.
Yeah, discrete Gaussian, exactly. So in that case, maybe you expect to see something like a Markov chain effective model between different winding numbers, right?
I expect that from 1/2 log n up to infinity. This
but I mean, at least in the case in which there's you have a discrete random variable, you have basically to take care only of a finite number of wells, right? So it could be
no. So the big problem. No, so let's say, okay, simple question. You start at 0, at zero winding number, and you let the dynamics run.
Yeah.
So I think the big problem in trying to show this Markov, that it converges to a Markov process, is that you need some type of local mixing near the minimum, right? If you start with 2 points near the minimum, near a local minimum, then they would mix before the exit time. This is what you would usually need.
Okay.
And for that, so you have to have some type of a priori estimates or okay. Already you don't have convexity. So if you start from 100 log n, then you could have convexity because you're in a smaller neighborhood. So you don't reach cosine loses convexity at pi over 2, right? But let's say you stay very close to 0, then you're convex. But then you need some a priori estimates, which are not that easy to get. And okay, the big problem is the high dimensionality. I think this is always the problem in these models. That when you have very large dimension, that okay, yes, everybody's pulled towards the minimum, but around the minimum is a huge neighborhood because the dimension is huge. I'm not saying it's not doable. We thought about it a bit. Okay, not enough to say that it's very difficult, but enough to say that it's not very easy. Yes, okay. The higher you take beta, the easier it is to get all these estimates, and okay, so the entropy becomes less important. So you can do rougher and rougher estimates on the volumes, and in the end, if you take beta, which goes to infinity and n fixed, then I think there are theorems that tell you, even without doing anything, just as once you know that the energy barrier is 2J, you cite someone and say that the exit time is exponential. I think this is. But if you try to work on the high dimensional in the high dimensional setting, then you need to be more careful about things. So.
Okay, thank you, Assaf. There is a question from Pablo.
Thank you very much. Very nice talk.
Thank you.
I am interested in the relation between this winding number statistical mechanics and the clock model that you put in your first transparency. The clock model is just the same, but you are somehow blind to the number, to the winding number. Is that right?
The clock model.
Well, the XY model, your first transparency.
So everything is okay. Let's go to the first transparent.
Yeah, this one.
Yes.
So here in the clock model, this I call clock model. No, it's called also clock model.
Okay.
Okay. So but here you are interested only in the cosines of the difference of neighbors, for instance. This one, yes.
Yes.
But in the winding number is more than that, right?
So, okay, maybe the thing to have in mind is that I'm working in the low temperature regime, so beta J is very large, which means that typically the angles between two neighbors are very small. Maybe as an intuitive thing. Yeah. So you could imagine that these endpoints are actually this field with this xi defined on a discrete torus. In some sense, could be thought of a continuous function from the circle to the circle.
Yeah.
And as a continuous function from a circle to the circle, it has a winding number. And this is our winding number. So I think that the intuition is really that in a low temperature regime, so large and high interactions, everybody is very close. Then you could approximate your configuration as a continuous function from a continuous space to a continuous space instead of discrete to continuous. And this function has a homotopy class, which is the winding number, and then you can study the topology of this thing. And in order to change a homotopy class, you need to break this assumption. So this assumption tells, under this assumption, the homotopy class is conserved and nothing could ever change. But to break this assumption, you need to create a discontinuity, and this is the energy barrier.
Okay.
Maybe this is the way to think about this. Yeah.
Thank you. Thank you. And what about the phase transition in two-dimensional XY model in large dimensions? Can you comment anything? Phase transition in a XY model in infinite volume?
Yes.
Your last transparency.
So okay, there is the dimension 2 and there is dimension 3 and higher, which are very different. So in dimension 2, again, if you think of instead of putting spins on the sides of Z, you think of a continuous function, but you allow some discontinuities because you're in a finite temperature, so you always have the option of having some occasional discontinuities. Then this space is R2 minus a few points, I know, minus x1 to x10, whatever. And this thing has a certain fundamental group, certain homotopy group, sorry. So function on this space have a certain topological, belong to a certain homotopy class. And then you ask whether or not the equilibrium measure is supported on the trivial homotopy class of the constant function, which comes down to the point of whether or not you have vortices in your system. So a vortex is a discontinuity point around which on all the circles, growing circles, you have a winding number 1 or -1 or something. So this is a vortex. So a vortex in a sense is, so the vortex structure could be thought of as the homotopy class when you take out several chosen discontinuity points. And in 2 dimensions, there is a critical temperature. And if you're below this critical temperature, you're not allowed any vortices. And above, you have many vortices that are completely mix your configuration. So this is the equilibrium transition. In dimension 3 and above, there is a classical phase transition where below a certain temperature, everything is aligned. It's just like the Ising model. So this is a classical phase transition where you have an order. In 2 dimensions, you can't have an order, so the spins could never align in the same direction in finite temperature. But you have this Kosterlitz-Salis transition where there is this topological phenomena. What does it do when you look at the dynamics? This is a big question. I think even in the physics literature, there are no clear answers of exactly how things behave. Okay.
Thanks a lot. Thanks for the talk.
Okay, last question maybe.
Can I ask a last question?
Yeah.
So it's about the following. So it's a little bit related with this thing about mixing in the wells. So when you condition to the winding number, do you expect the measure to be something like a Brownian bridge?
It's exactly a Brownian bridge. Yeah. It's
exactly a Brownian bridge. Okay.
This is how we prove. Okay, so sorry, it's here. The part with the normal random variable, y random zero. I show the heuristics with this minima, but the way we prove it is because when you have nearest neighbor interaction, this is exactly a random walk, right? So the measure is a random walk conditioned on ending at an integer point.
Mm-hmm.
And if you know which integer point it is, then it's going to be exactly a random bridge with transition probabilities that are something strange, like a Bessel kernel or something like that. But yeah, it's the equilibrium. This is the reason that the equilibrium is very simple, and that we say that one-dimensional models are trivial because in some sense they all look like random walks, which
Okay, thank you.
Okay, so I guess we can thank Assaf again. So thank you very much, Assaf.
Thank you.
And see you next week.